I'm going to go over some of the technical aspects of our design. Like as Josh mentioned, first we're going to be a pre-treatment section, just to build up the switchgrass biomass component to a workable gasification feed stream. Next is gasification, and then that produces syngas, which will then be syngas fermented in a biocatalyst reactor, and then the purification stage to purify our ethanol. So first, gasification is our first process stage. The chemical reaction is basically right there overall, and they are endothermic, and so they primarily consist of pyrolysis, which degrades biomass into immediately into high temperatures, and then the gasification reactions consist of char reduction and water steam gas phase shifts. So to do this and to suit our endothermic overall reaction, we're going to use an indirectly heated steam fluidized gasification reactor. And our fluidizing medium, we chose steam for several reasons. One, because air, they have several noxious byproducts with that, with the increased nitrogen content. And so you can see the air heating value product also produces, with steam, produces a higher heating value. And so to do this, we're going to be using an allothermal position to provide the heat. And our heat transfer medium will be olivine. It basically is a medium composed of magnesium and silicate. And we'll be flowing that into the fluidized reactor with steam to provide our heat for the endothermic reactions. Next, some properties of our further of the gasifier reactor. Some design considerations: our steam to carbon ratio is very important, especially your steam flow rate to your carbon flow rate to the biomass content. And also your olivine feed is very important to provide the correct amount of heat, which is fed from the steam power generation combustor. Next, our desired product syngas flows is a very specific property, is a design parameter specification specified by us, which was 2,000 kilograms per minute output of the syngas. And from that, we can find our switchgrass feed rate from that equation right there, multiplying the output by the lower heating value of the gas, which was a composition I'll go over later on, which was the lower heating value found through that. And the efficiency of the gasifier multiplied by the lower heating value of the feedstock itself. And to do this, again, really important, just as well as heat transfer, another important thing is the mass transfer, which in our pre-treatment stage we come to a particle size of close to 10 millimeters. Next stage is syngas fermentation. We'll be using a continuously stirred bioreactor here, and basically we'll be using an anaerobic microbial catalyst in the acetogen group. Clostridium lentiginale is the name of it. And basically, broken down microbiologically, it will also be fed with an ethanol-favored reducing agent in the culture medium with about 30 parts per million using benzyl viologen. And what this does is it increases the electron content, or the H plus content, and it favors the C1 carbon electrons that favor ethanol production. And some of the design considerations that dictate our fermenter design is, of course, agitation speed. That increases our mass transfer between the gas and the liquid culture media, the biocatalyst. And, of course, some considerations in optimization will be energy requirement involved with that. And also another considerations are syngas flow rate. Now to go over through the main stages in their design, I'm going to go over some of the design analysis, the way we approach this in our procedure to provide a basis so we can approach our material balance and energy evaluation of each stage. First, switchgrass feed. We obtain an ultimate analysis through our research, and basically that breaks down into a formula we can use and break down into in our mass balances. CH and O, biomass. Switchgrass is composed of three main constituents. It's cellulose, hemicellulose, and lignin. And that breaks down, we can use a simple formula like this, and a stoichiometric model is formed from this equation right here. X is being the molar amounts stoichiometrically, and using some computation factors such as our steam to carbon ratio, our switchgrass composition, in our water to CO2 ratio, we can have 5 equations, 5 unknowns, using stoichiometric relations, come up with a working reaction for that. So some design parameters are important first for our pre-treatment stage. In order for the gasification process to be effective, a reduction in size obviously is sort of as needed. Smaller the better, obviously. This reduces a greater bond index, which will have an effect on the price. Also needs to be large enough for setting of dry biomass to pass through the ball mill before beginning to reduce in size. Pre-treatment, again, the ball mill shows it for the fact that it has been shown more effectiveness, the size breakdown of the switchgrass. Again, opening side of 10 centimeters is the best, which then the switchgrass size of 10 millimeters was chosen for us. And this will result in a bond work index of 30 kilowatt hours per ton of the biomass. Next, for the gasification stage, some of our specifications, we assume the gasifier efficiency, this is, through our research again, is about 70%. The lower heating value of the switchgrass, again, from the ultimate analysis was 18.7 megajoules per kilogram. Lower heating value, again, with the syngas, produced again from steam as opposed to air or oxygen, is 14 megajoules per kilogram, which is a medium lower heating value. The steam to biomass ratio we had was 2.0. Our desired product gas flow again was 2,000 kilograms per minute. And switchgrass feed, this came through our mass equation, was 2,200 kilograms per minute feed. And for the purification stage, we'll be using a distillation column, constant feed rate desired, mole fraction of distillate. We have 450 kilograms per hour total. Mole fractions of this will be 0.8 water and 0.2 ethanol. Some of the variables to consider in our design are the number of stages, obviously, which Josh will talk about further later, the bottoms flow rate, and then again some of our optimization results in 20 stages. Bottoms flow rate at 275 kilograms per hour. Next, Brian will take over with some 10 cab models.